Good evening, dear students. So we are back to the fourth session of our class. Today we will see two very important terms. The first one is acceleration due to gravity. That is the equation for acceleration due to gravity. And next we will talk about this orbital velocity. Okay then. As the law of gravitation says, if this is the mass of the earth, m be the mass of the earth, and you have another body here, you can keep here, maybe a solid sphere or something whose mass is m, let us say. Then when you join center to center, you should be joining like this here, center to center, and the radius of the earth, let us say from here, this is the radius of the earth, this mass. So you have another sphere or a ball or something whose radius is negligible. Let us say r be the radius of the ball, and the capital R stands for radius of the earth here. So when you make comparison, radius of the ball is very less as compared to radius of the earth. This is the reason why we neglect this portion here. We used to neglect it. So when you write the laws of gravitation, it becomes F is equal to Z, the two mass m divided by square of the distance. So as I said, radius of the ball is neglected. So the exact distance is taken as equal to radius of the earth. So you can write as r square. I repeat again. We are neglecting the radius of the ball or the body you keep, since the radius is very small as compared to radius of the earth. Then let this be equation number 1, and one more, F is equal to mz. This equation comes from the relation F is equal to ma. Force is the product of mass and acceleration. But in our case, this body is under the action of gravity. That's why this acceleration is replaced by acceleration due to gravity. So this is your equation number 2. So when you make comparison, because both the two equations represent force, you can equate them. After equating, you have mz is equal to zmm divided by r square. So these two cancel, leaving z is equal to zm by r square. This is the equation for acceleration due to gravity. Now, coming back to the earth. The mass of the earth, this is approximately 5.98. But this is generally taken as about 6. But let's just take it as 5.98 into 10 power 24 kg. It is the mass of the earth. And the radius of the earth is about 6400 kilometer. When you change it into meter, 6400 multiply with 1000 meter here. Then this z for universal constant, whose value is 6.67 into 10 power minus 11 SI unit. So once you put all these values here, after you substitute all these values and do calculation, like put z is equal to this value, mass of the earth, put this value, radius of the earth, put this value here. So this will be equivalent to 9.8 meter per second square. So this is the value of z that we use in almost all the numerical calculations that need to find certain quantities which is related to what? This gravity and all. In other words, this value g is equal to 9.8 meter per second square. This is a value that is used very commonly in numerical calculations here. Okay, this is all about a short introduction. So now it is very clear that gravity depends on mass here, because g and the m, these two are having some relation now. What is the relation? Directly proportional here. It means if you increase the mass of the planet, gravity also increases. That's why those planets with bigger mass, they used to have more gravity. And those planets with smaller mass, they used to have smaller gravity here. This is the relation between mass and this acceleration due to gravity. Okay, this is the brief introduction about the acceleration due to gravity. Now let us move to the other part, that is orbital velocity. So in the last class we had already seen the escape velocity that I already sent to you about the escape velocity, and the escape velocity of Earth, it was about 11.2 kilometer per second. So like that we'll be talking about this orbital velocity. Let us see what is this. Denoted by VO. If this is the Earth, imagine there is a tower very high, say thousands of meters, let us say. If you throw a stone, standing at the top, you just throw a stone, this will fall here. The more velocity you throw, this will increase like this here, keep on increasing here. So if you can throw with a very great velocity, then the body will not fall on the surface, but instead this will go around like this here. This will continue to move all the time around if you throw with a velocity. So that velocity needed by the body so that it may continue orbiting around the Earth, we call it the orbital velocity here. Okay. It means you need to have a velocity. What velocity? With the velocity, if the body has this velocity, the body will continue to move around. So that velocity is known as orbital velocity. Definitions and all, you please check the web page that I sent to you. Everything is there. And even the derivation is also there. So what we are doing is just a brief explanation of the derivation. Now, let us try to derive it. If this is the Earth, let this be the center, radius of the Earth be r, and let us say here is a body that you want to go around. It may be a satellite. As we know, satellites continue to move around the Earth. So let this be the body here, or the satellite whose mass is m, let us say. Then this satellite be at a height of h, let us say. And remember, it has to go with a velocity known as orbital velocity. It has to go around. And the big letter m be the mass of the Earth. Then between this mass of the satellite and the mass of the Earth, there must be a force of attraction that is given by Newton's laws of gravitation. So from Newton's laws of gravitation, F is equal to Z. The two mass you have is m and the mass of the satellite. So you can write m divided by square of the distance. Right now if you see, this is the height of the satellite. So the actual distance becomes r plus h whole square. This is your equation number 1. And when a body is describing a circular motion, let us say this is the body of mass m moving along a circular motion, with the radius r with a speed of v. There is a force that makes the body to go around like this. I repeat again, there is a force that makes the body to go around, and that force is directed towards the center, and this force is what we call as the centripetal force. So the centripetal force F is equal to mv square by radius is what? R. Keep in mind, this is the centripetal force. Centripetal force makes the body to go around. If there is no centripetal force, this body will never go around like this. So like this, in this satellite also, the body is going to go around. It means there must be a centripetal force. So this centripetal force will be given by F is equal to, using this formula, the mass is m here, mv for the orbital velocity, so it becomes mv o square by distance is what? R plus h here. Equation number 2. We have two equations now. And remember, in the case of a satellite, I repeat again, a very important statement. The force of gravitation between Earth and the satellite, it provides the centripetal force required by the satellite to go around here. It means, I told you that there is a gravitational force, attractive force is there. So that attractive force will provide the necessary centripetal force. In other words, these two equations 1 and 2 will be equal. Simply because these two equations represent what? Force here. You can go either way also, no problem. So equating 1 and 2, or simply keep in mind that centripetal force, this is going to be equal to what? Gravitational force. These two should be the same. So now if you compare this, you can write mv o square by r plus h. This is equal to z m by r plus h whole square. Okay. Then we'll cancel these two, and this is a cancel. So after cancellation, you are left this quantity VO square is equal to ZM. I cancel these two, this also. So ZM by R plus H here. Only this is left now. And just now I told you that acceleration due to gravity is given by Z is equal to ZM divided by R square. So this will give you Zm is equal to cross multiplication. You will get Z R square. So this value I am going to put here. Therefore your orbital velocity, it becomes Z R square divided by R plus H here. Or you can write VO is equal to square root of ZR square by R plus H. Okay, this much we have. Then let us come to one important note. In the case of Earth and the satellite, let us say this is the Earth with the radius of R here. When satellites move around the Earth, generally satellites move closer to the surface of Earth here. Height of the satellite is H. I told you that H stands for height of the satellite. So normally height of the satellite is very, very small as compared to radius of the Earth here. So conclusion is, radius of the earth should be much greater than height of the satellite. It means we can neglect this h here. You can neglect this h. H here. You can neglect this. So neglecting h, what do you have? VO is equal to square root of GR square divided by R. We have this. So finally you have orbital velocity is equal to square root of G and R here. So this is the equation for orbital velocity. So now we can see orbital velocity, it simply depends on acceleration due to gravity, and it depends on the radius of the planet. And orbital velocity does not depend on the mass. VO does not depend on mass of the satellite. Okay, this is the important formula that we have derived. So from this we can calculate the orbital velocity of a satellite if it is supposed to move around the earth. So in the case of earth, let us say for earth the value of z is 9.8 meter per second square, and the radius of the earth is 6400 kilometer. This is going to be 6400 into 1000 meter. So put it now in this equation. Therefore VO becomes square root of Z. I'll be using this 9.8 into 64, let me write 0 into 3 and 4, 10 power 4 here. Let me write like this. Alright, there was some technical problem, so there is a slight jump in the video. That's okay, fine. So let's come back to the equation again. So we have this 9.8 into 6400. So I just take it out, this 10 and these two zeros cancel. So you are left with this 98 into 64. It becomes, when you multiply it, you will get 6272 into 10 power 4. So when you take square root of this, you may get 9.1 something, 19. Let's just take it 7.9 here into, when you take square root of this, only 10 square is left. Okay? So now, this will be in terms of meter per second here, because this is your orbital velocity. Then simplify it a bit further. Let's write in the long way. 791 by 10 into 2 zeros. These two cancel one more time. So we are left with 7910 meter per second. So if you convert into kilometer, this will be 7910 divided by 1000. If you convert into kilometer, so meter converting into kilometer means you need to divide by 1000. So you have 7.91 kilometer per second. It means if your satellite can move with a speed of 7.91 kilometer in a second, if the satellite can move with this much speed in a second, it has to move 7.91 kilometer. Then the satellite will continue to go around the earth. This will never hit the earth. At the same time, this will not go away. This will be moving around in a fixed orbit. So this orbit will be called as geostationary orbit or parking orbit. You can call it as a parking orbit here. So this is all about the orbital velocity. So now I repeat again, orbital velocity does not depend on the mass of the satellite. So if you have two satellites, one satellite is having say 100 kg, you have another satellite, bigger one, it has 10,000 kilogram here. One is 100 kg, the other is 10,000 kg, and you have one more satellite, only 1 kg only. They need the same orbital velocity. It doesn't mean that 1000 kg it needs more orbital velocity. It's not like that. Maybe large or small, they need the same orbital velocity. Why? Simply because orbital velocity does not depend on the mass. There is no equation of mass here. No mass means orbital velocity will not depend on the mass. But orbital velocity will depend on the gravity. More gravity means satellite need to move faster. Why? Because gravity increasing means orbital velocity also should be increasing here. Suppose if the gravity of the say if the planet is say G for example, now at this time satellite is moving like this here. Okay, at this speed. If gravity suddenly increases, it needs to go faster here to maintain the orbit here. If gravity is becoming less gravity means satellite will move slowly here. Gravity increasing means it has to go faster in order to continue in the orbit here. Okay, this is all about the orbital velocity, and I hope you enjoy the class and you can understand what I am explaining. So if you have any confusion regarding these things, you don't mind to send questions to me, and I'll be glad to help you. Okay then, I'll be seeing you in the next 5th session of our class again. Okay, thank you for watching.